Starting off from where I left y'all, Q is equal to CV, right? That is the equation we came up with. Studying about capacitors. So what is a capacitor? Two plates that are separated by a short distance. It could be air or it could be a material. Now, if the plates are too close, then it can't take too many volts across the plates, because if the plates are too close, then even a small voltage will actually ionize the air in between, and then sparks can run through it and damage the dielectric material that is put over there. So capacitor can be damaged easily that way. So the voltage is a very important concern. Capacitance is an important thing as far as the circuit calculations go, but the voltage of the capacitor is supposed to be something that is a concern. Now, if you exceed the voltage, then it blows up like that, and that's why the provision is there for it to blow. So I'll pass this. Now this is the one which is not blown. I sent two bad capacitors, two blown capacitors last time, and only one came back. See if there's anything around there on the floor or something like that.
You steal it. Johnny stole it. Johnny.
Donovan Vogt is the culprit. Donovan Vogt is the culprit.
I don't think it's come here.
I'm not that big up. No, do not that
Someone must have swallowed it. Anyway, a good one will have absolutely flat edge. That capacitor was picked up from this television. There are some bigger ones which were blown as well, but the smaller ones are those. So totally around 6 or 7 capacitors were replaced of that size. Okay. So you can see what happens. Now, how many volts does it indicate? How many volts is it? 10. 10 volts on that circuit part. Probably the voltage, the voltage which flows into that circuit at that spot could be close to 9, around that much. So having a 10 volt capacitor over there is inviting trouble, because if there is any slight voltage surge, which is very common, one lightning can cause power disturbance, and that power disturbance can cause a spike in the voltage. And that is enough to cause one capacitor to blow up and short circuit. And once it short circuits, many other capacitors in the chain will actually also get affected. So that's why around 6 or 7 capacitors were blown up. And as soon as I see a blown capacitor, that's a good sign that you can fix it fast. But if there are no signs of any blown capacitors, then it could be more on the transistors getting spoiled, or the chip itself is like burnt inside, which cannot be seen externally. And if the chip itself is burnt, then replacing a chip is going to be very, very hard. So instead what we do is we look for a board, cheaper one, and then substitute. Okay, so that's what we do. So capacitors, what I put over there instead were 16 volts capacitors. Instead of the 10 volt, I put 16 volts. And now no problems at all for that. 16 volts, it can sustain any surge and other things. So manufacturer's defect is what I'll call that as. Okay, so we have capacitance as Q over V, and we went through the unit of capacitance and all those things, right? Now, looking back into the parallel plate capacitors. Parallel plate capacitors, when you charge it with a potential difference, when you charge it with the potential difference of V volts, and if the distance between the plates is D, the charge acquired is Q. And let's say it is air in between, just air or vacuum in between. what happens is there's a field that is actually set up inside. There's a field that is set up inside the parallel plates. It's a uniform field. Now there is a connection. So there are flux lines here. The flux that is actually passing through, flux that is moving from there to there is connected. I think we've done that already. What is the flux equal to? Check back and find out. What is flux equal to? The charge enclosed over. Go back to the flux and find out what is flux equal to.
EA cosine
Say it again.
EA cosine
EA, yes, flux is EA. Flux is EA, but what is flux itself?
gravity field lines.
Don't you have this equation?
Yes.
That's what I was asking for. In terms of charge enclosed, so when the charge is Q and relative, the permittivity of the space is epsilon naught, flux is this, which means EA is Q over epsilon naught. And what is E in terms of V, D, and all that? What is E? Yeah, what is the connection between E and V and D in the parallel plates?
Negative field.
Good, potential gradient. I'm not going to put the negative sign. V over D, A, is equal to Q over epsilon naught. Oops. V over D times A is equal to Q over epsilon naught. Now if you cross multiply this equation, we have Q is equal to A epsilon naught over D. Or V epsilon naught A over D. The same thing. Just rewriting it this way. And if I divide both sides by V, I have Q over V is equal to epsilon naught A over D. What is Q over V? C. So the capacitance of this capacitor is equal to epsilon naught A over D. So you can see what are the factors affecting the capacitance of a capacitor. Factors affecting capacitance. Factors affecting capacitance. Looking at the parallel plate capacitor, what are the factors that actually affects the CE?
Area density.
Area and not density, the gap, the separation. Area, that's right, area of the plates. Now when you say area of the plates, area common area. Basically, common area means area of overlap. Common area means area of overlap. Okay? Like you can have two plates like that. If there's no overlap, then there's no area. Now like this part is the common area. Did you get it? So if you have two plates like that, the common area is just the area that you have to look into is this one. Now if it is like that, of course the whole area. Okay? That's a common area of overlap. And the other factor is separation. And obviously when you're having a capacitor, you don't have to have it only air capacitor or vacuum. You can put some material there that will change the permittivity. So if you put some material inside, then C is equal to epsilon naught epsilon R A over D. Epsilon naught epsilon R A over D. And the book calls epsilon R as K. Okay. So what is epsilon R? Epsilon R is relative permittivity. also called as dielectric constant. And that's what they call it K. So this equation can be written as epsilon naught epsilon r A over D or epsilon naught K A over D, where K stands for dielectric constant. We used to call that as relative permittivity. That's right, that's a real thing. But here it's called dielectric constant for a reason. Because when you put some material inside, that material that you're putting inside should be an insulator, because you don't want these two terminals to be short-circuited. So it should be an insulator, and when you put an insulator in an electric field, the molecules or atoms will get polarized, rearranged. So when they get rearranged, you get two poles, like positive, negative, positive, negative. That's why it's called dielectric. So when you have a material put inside, that material will get polarized and it will create two poles, plus minus, inside. And that is why that constant is called dielectric constant. It's the same thing as epsilon r. So in this chapter, you'll know it more as a dielectric constant than epsilon r. All right, so epsilon r is also important, dielectric constant. So the factors affecting C, epsilon naught is a constant, so we're not considering that. Dielectric constant, call it K or epsilon r. So we have three of them: area of plates, separation, dielectric constant. Now, how can you make C as large as possible? The purpose of a capacitor is to make it store more charge. That's the purpose of the capacitor. You want to get more charged up, and so it can hold more. It has more charge capacity. That is the purpose. So how can you make C as large as possible with these things? Right. Make the area as big as possible. That's true. You make the area as big as possible. So if you're looking at a capacitor like that, the area of the foil that is kept inside, it will be pretty long. If I unroll it, it will go all the way, long distance, for this one. So the area of this one's capacitance is 6,800 microfarads. So it's a big one. So you'll find the area also very large. That's one factor. Yes? You can minimize the distance between the plates, which is this one. You can minimize the distance between the plates, but you know the consequence of minimizing the distance between the plates? You have found it?
Yeah.
Where was it?
Okay.
But what happened to the color? Someone peeled it off. Yeah, this is. Yeah, it is almost gone. You can see that. Yeah, so if you open up those capacitors, you will see a long, aluminum foil group. So it's kind of wound around, and that's why it's pretty hard. Now, the separation is an important factor also. So if you get it too close, the problem with that is you cannot make it higher voltage. You get it? If you want to get it higher voltage, then you have to keep the caps more. Now this one here is a capacitor. This can take 450 volts. You can see the size of it. Why is the size bigger? And how much capacitance is? Only 220 microfarads. It can only hold 220 microfarads capacitance-wise. So the capacitance is not too big, but the voltage is big. Why is the voltage big? It's because the gap is bigger. The gap is bigger, it can handle more voltage. It can handle up to 450 volts. But the capacitance, how much charge it can store, is less. Only 220. Look at that capacity. It says over here 4 volts. This can only handle 4 volts. But 560 microfarads. 560 microfarads. This one was only 220 microfarads. This is 220 microfarads. This is 560 microfarads. Look at that. It's able to handle more, but the voltage is only 4. So if you give more than 4 volts, it will pop. Now this is also 560 microfarads. This is also 560 microfarads. But this one is 200 volts, but this is only 4 volts. Right? So, well, the purpose of, technology itself is like shrinking. So you're trying to minimize the weight of the device. You're trying to minimize the components, sizes, and everything together. So what happens is probably because of that. They try to choose smaller capacitors, so like 10 volt capacitors, when they could have chosen 16 or 25. By not choosing 16 or 25, they chose 10. Thereby what happened is the weight of the television will be low, because you have so many capacitors and they're all lighter. So there's a big difference there. And that is one of the reasons why they don't go for bigger components. Safest thing to do is, if there is a place where I need to put in 200 microfarads capacitance, and I have, like, suppose the required voltage or the accepted voltage at that spot is 25 volts. Okay. Now, when I look at my spare, I'll see one for 25 volts, which is appropriate. That's exactly what it is supposed to be. But I also see one for 50 volts. So which one will I choose for that particular purpose? I'll go for the 50, because I know it's not going to blow up. That's for sure. So that's pretty much what I did in the television. I put capacitors in which were all on the higher voltage side. That means even if there's a power surge, that is not going to go off. Okay? Yeah, there was a little space issue, because when I'm putting a higher voltage capacitor, it has a bigger diameter. Okay, so that means I have to like put it properly, because there was less space. That was a challenge. But after that, there was nothing else. Once I could just fit it in, then there's not a big issue. If there's no space, you can put it from the other side of the board as well. You can just put it from the other side of the board. That should work if there is a sufficient space available. Now, dielectric constant. Dielectric constant is this one. You can actually put a material. It has to be an insulator, so you can put a material like paper, mica, and all those things. Paper, mica, glass, all those things are going to increase the capacitance by only like 5, 4. Now water has got 81. I think I told you that, right? Water has a high dielectric constant. But how do you put water between the plates? So if you put water between the plates, okay, now first of all, it has to be pure water. Okay. Now once you put pure water between the plates, how will it remain pure? It's not going to remain pure. You will get some salts and all that picked up, and after that it becomes a conductor, and that's enough. So having water there is not a very convenient thing. So there has to be something done to make it have higher capacitance. Now there are capacitors such as this. These are also capacitors. These are all in the picofarad range. Pico means 10 power negative 12. What I'm talking about is micro, and this is pico. Pico is like 1,000,000 times smaller than micro. So these are also capacitors. That's also capacitors. So basically it says 474 kilo picofarads. Kilo pico means nano. So it's fine. Capacitance. So yeah, these are smaller capacitors. Now what is the difference between this one and these ones? These ones have no polarity. There's no plus minus. So what's inside here is pretty much these terminals. The terminals go like that and they just stand like that. That's it. Those are the plates. Sometimes the terminals themselves are the plates. Do you understand? So that's why it's got only small capacitance like picos. This one is an electrolytic capacitor. It's formed through a process of electrolysis. That's why this terminal is indicated with the minus sign, and automatically the other terminal is positive. Okay. So you can see on all capacitors, you can see a minus sign indicated, and that is the minus sign. So we always look for this to find out which is positive, which is negative. That will be an issue on this if someone removed the cover. Now, God knows which is positive and which is negative. Because you see, it is two terminals, but I don't see anything here. I can't actually figure out which is what. So yeah, the covering actually will tell you. Most of the time they put the minus signs, indicate the minus signs, and then some of them put plus and minus, or some of them just put plus. Mostly it's minus though. Most of them are minus. Here, you can see minus sign indicated there. Yeah.
So like in TVs, what function do capacitors serve?
Capacitors have multiple functions in a circuit. Capacitors can do sort of filtering, alternating fluctuations. So it's basically used to filter the alternating fluctuations and make sure that it is DC. Capacitors are used in adapters. So if you look at any adapter, you'll see capacitors used there. You know what I'm talking about, adapters, right?
Yeah.
Yeah, I'll just open it up and show you what is inside this thing. You see a capacitor sitting inside. That capacitor has a function over here. That is, it's 110 AC coming in here through the transformer, which we'll study later. The transformer actually steps it down from 110 to like how many volts are going to come out here. So yeah, this has got multiple voltage choice. You can choose the different voltages. You can see. So you can get 1.5 volts here, 3, 4.5, 6, 9. You can choose whatever you want by just sliding this. That's why these transformers are special, because they got multiple terminals. Anyway, that is a function. Not all adapters are exactly like this. Some of them are like straight. Okay, 110 goes in here, 6 volts comes out from there. That's it. But the 6 volts that's coming out from there is alternating. And so a couple of diodes are used here to change the alternating to DC. So instead of alternating like this, they make it like that. Just peaks. And the capacitor that sits here is what makes it almost like flat. How does the capacitor do that? The capacitor, as soon as it gets a first voltage coming in, it charges up. And then when the voltage goes down, the charge is still held on to it. Therefore, the potential difference, it will hold. So since the voltage is held, instead of going up and down like that, the signal won't be jumping up and down. It will be like flat. A little fluctuation will be there. Depends on a good capacitor. Now, if I put a much better capacitor here, it will filter it pretty well. Capacitor, this is the same thing I used long back when I got my job, 1984. They gave me a 3-bedroom apartment, and what am I going to do with 3 bedrooms? I only used one. The other rooms were barely free, no curtains, nothing. I just didn't bother. So only one room, and that's where I had my tube. And even the tube light was not like this. I wanted to put a light, and so I said, I'll put on a tube light. And then I went and bought the tube separately, and the choke separately, and the starter separately, all separate. And then I clipped it onto the wall. Clipped the starter, the choke, everything on the wall. Clipped the tube also on the wall. Then I used normal crocodile, the gator clips, and connected it all. And that's my, tube light. It was on the wall. Yeah, pretty interesting. Like people come in, what is that? I said, that's the tube light. And you can see the clear circuit diagram on the wall because that's exactly how it is here. Now this is all enclosed. You don't even see the starter. You don't even see the choke, nothing. But there you can see all the components clearly. That was how I had my, I tried to minimize things completely and just use exactly. So there was a need for the calling bell. People keep, hitting the door. I said, calling bell required. So what I did was, I didn't want to go spend money on a calling bell. What I was thinking of was like try to reuse something that I already have. Can I make it into a calling bell? So what I did was, those birthday cards and Christmas cards, that when you open it, it'll sing. Mm-hmm. So I took a Christmas card. When you open it, it sings Jingle Bells. So what I did was I attached a small amplifier from all the scrap that I had. Small amplifier, just one transistor, one capacitor, and one resistor. That's it. It's already an amplifier. And then I used an adapter like that to, get the power. So I did all that stuff, and the switch was placed outside. Now, when you press the switch, what happens is, the switch has to be pressed for long if you want the song to go on. You have to press the switch, then it will sing. Now, who is going to press a calling bell for long? So just press and leave, right? So it'll just ching. That's it. The jingle bell is not played fully, like ching. And then all I hear is a little spark kind of thing. So I said, okay, now I need that to sustain. If anyone presses it, I want it to sustain for some time so that the song will play. So I went for a capacitor. So when someone presses the bell switch, it's like a capacitor getting fully charged straight away. So the capacitor connected to the bell switch, and that's a power supply. Okay, and then I put a resistor here, and also I think I put a relay also here, and then coming out from the relay was my bell, the jingle bell thing. So the moment anyone presses this, even for a flash, the capacitor will get fully charged, right? And since the capacitor is fully charged, the voltage over here is going to be full. So if it is 6 volts, it gets full 6 volts. And the relay stays held. And so the bell will continue to ring. And this voltage will slowly go down, discharging. We'll talk about discharging later. The voltage will go down slowly here. And so the relay will also the relay needs a certain voltage to keep itself active. So once the voltage here drops below that, the relay will cut off and the song stops. Get it? So how long do I want the song to go on depends on the choice of this resistor and capacitor. So we can actually set up timers. So timing, all timing circuits, all timing functions, capacitor is the main brain behind. Right? Capacitor is the main thing behind it. Anything that you want to time, even a time bomb, is the capacitor mainly. Capacitor, resistor, combinations, battery. Yeah. And when I was teaching this in the Middle East, when I said all the other functions, they were all keeping quiet. When I said time bomb also uses, how do I make one? Immediately they were more interested in making that rather than bells and stuff like that anyway. So I said, no, that is dangerous. Even if it's a simple circuit, I don't want to share that information. I said, okay, then I kept that away completely, yeah. Yeah. Yeah, you need to make that. All right, so did you get it? So you have that function, you have adapter function, and so many functions. you'll get to know gradually. All right? Right now you're learning about a capacitor, and then later on you'll start finding out where is it used and how it's used and all that. One use I already showed you as a filter. This is a kind of filter capacitor. It filters. So that is an electrolytic capacitor. So the capacitors are two types. One is non-polar capacitor, which is normally a small value, and then you have an electrolytic capacitor. It's called electrolytic capacitor because it is formed by a process of electrolysis. That's why it is called electrolytic. Now, how can you connect this? You can connect this way or this way, it doesn't matter. But this one has to be connected positive, negative properly. If you wrongly connected, it's going to be you can leave it here. Leave it on the table. All right, so electrolytic capacitors, they are created by applying proper voltages, and then in the process of electrolysis, you get this capacitor formed. So when you connect it, you're going to make sure that it is like positive is here and negative here. If you switch it around, it will destroy the capacitor again. I'll tell you what it is. Any questions on this? So electrolytic capacitors have large capacitances. You saw that 6,800, 2,000 microfarads and all that. It's a large one. And how do they achieve that? Not just by the area, not by dielectrics, mainly by the separation. Mainly by the separation. So how is an electrolytic capacitor constructed? Yeah, you'll find so many things, like you'll be prompted to ask so many things, about these things, like how is the capacitor used in this function, all that. But we'll get to those topics. Right now we are doing basic electricity and capacitors and stuff like that. Then you do a basic, more about electricity, and then after that you will see how capacitors and resistors get together. Okay. Now here is a variable capacitor. This is a variable air capacitor. Okay, can you close it up? Variable air capacitor. Now why is it called air capacitor? It's because the gap is filled with air. Now where is this thing used? It's actually part of a radio. There will be a string running here and then going to the knob. So when you turn the knob to change the stations, have you controlled those radios? There will be a pointer, and you can just move it by twisting it or rolling it, whatever. That rolling action is this. And you can see the plates coming out and going in. Can you see that? These are semicircular plates, and there are multiple of them connected together. So basically what is here is two sets of plates in the shape of a hemisphere. There's one set of plate here, that's also a hemisphere, and this is also another hemisphere. So if the plates are totally not together, there's no area. So as you start rolling into the other, the common area of overlap will start coming in. So the more and more it goes in, the more and more the capacitance. You get it? So that's why it's a variable capacitor. When you keep it here, completely everything is out. This is the rotor, and that is a stator, like stationary. That's stationary. So when I move it like that, you can see the capacitance increasing because it's moving in. And although it is moving in, they don't touch the sides. And what is there is air. Well, this is defective because it is touching. So it's basically shorting. You can hear it. You can hear that, all right. This is a revelation. All right, so this is a variable capacitor. I'll pass this around and then you can actually have a look at it. This is part of the radio. So in a radio, the main components of the radio: antenna. The signal from the antenna goes into a capacitor, inductor circuitry, and when you change the value of the capacitance like that, you tune to different stations. Okay, how do you tune to different stations? Is because when you change the capacitance value here, you are actually changing the resonant frequency of the circuit. When you change the resonant frequency of the circuit, you can actually match up with other frequencies, the carrier signal frequency. So if you know that 970 is on this frequency, then you can change it and put it exactly matching with that frequency, and then your radio receives that signal. So this is basically a variable capacitor, and it is air between. Okay. So yeah, capacitors are kind of put into so many uses, and every time you'll see that every time you come up with some questions like that, I will end up saying, we'll get to that later. Okay, we'll get to that later. I will always keep saying that, we'll get back to that later. And since I was using this so many times, we'll get back to, so students are interested in knowing more, but I know this is coming after 2 chapters, so why should I start working on that right now? So the best thing to do is, I'll get back to that later. And eventually, a couple of years ago, some seniors decided to give me something so that I can press the button. I can press the button and it'll say, we'll get back to that later. So instead of me saying it, as soon as it comes to that place, I just press the button. And so they gave me this. They gave me this one. So all I have to do is keep it there. And as soon as, Alex is going to ask me, like, what about this, bang. And it'll say, we'll get back to that later.
Okay.
Yeah, so but then I used it for a different function after that. I kept it like that for some time. And then after that, I used it for a different function. I rarely take off from school, you know that, right? So the only time I took off, I knew there was a substitute teacher coming in. I just wanted to give a surprise to the substitute teacher. So I kept it right on my desk. And look what I wrote on it. What is it?
Don't press me.
Don't press me. Okay? And I know that anyone reading this will say, what will happen if I press? I just go ahead and press it and see what happens. Because if it says don't press me, everyone is tempted to go and press it. That's normal human. If it says wet paint, don't touch or whatever. Really? Is it wet? Oh, yeah, it is wet. So you want to test it that way. So what I did was I put this right on my desk, and I'm sure, it'll create some kind of a fun activity for that substitute teacher. I don't know who was coming, but I left it there. And then I got an email from him saying that, it was so, weird that he said, don't press me, and I ended up pressing it, and this is what he heard. Okay, so he was like, he pressed it and he was waiting for some, how dare you touch me? So that's what I recorded instead. And he was so excited, he kept it pressing, and then he recorded and took it to his wife and all that stuff, which was pretty interesting. Yeah. So, okay. All right, so capacitors, now, capacitors are used in multiple places, so remember that part of it. Now, how is an electrolytic capacitor formed? Electrolytic capacitor is formed by taking 2 plates, just like normal, and they put waxed paper here. Not waxed paper, sorry. Paper that is soaked in aluminum borate. Aluminum borate. So this is a paper soaked in aluminum borate, and it is kept between the plates. And then you pass electricity. So when you pass electricity through this thing, what happens is electrolysis procedure goes on, and then there'll be a fine coating of aluminum oxide as a consequence. There'll be a fine coating, a powder coating. A powder coating is so thin, right? A very thin powder coating is formed right there. And after the electrolysis, the powder coating will stay there, and the rest of the electrolyte becomes a good conductor. this will act as if it's just a metal, aluminum. So this coating here and all this is metal. So it's basically like taking this and pushing it all the way. You understand what I'm saying? If this whole thing is a metal, if this whole thing behaves as a metal, joined with this, so isn't it like pushing this plate all the way till there, like that? And what is separating it is a powder coating, and the powder coating is very, very thin, and it is uniform. Yeah.
But the powder is an insulator.
There's an insulator. Good question. So this will be an insulator. The rest of it becomes a conductor, and so you are able to achieve a very small separation. And that is formed by the process of electrolysis. That's why plus and minus will be indicated. So what will happen if you flip it around? The aluminum oxide coating will be kind of undone. You know, it will rip off this, and therefore it will damage the capacitor. So that's why electrolytic capacitors should be connected in a certain way. So this is the procedure of creating electrolytic capacitors. Aluminum borate. This is the pen. Where do we click? Oh, stop.
Yeah, got it. Okay, thank you.
I thought I put a wrong number, but it's worked. All right, so electrolytic capacitor, aluminum borate, through electrolysis, aluminum oxide formed. Aluminum oxide coating is a very fine coating. It is almost as if the D is so many micrometers. You can't achieve that by papers and all that. And that's why the capacitance is on the higher side. So you can actually create capacitors in 1,000, 2,000, 5,000 microfarads. Whereas if it is just a normal capacitor like this, you can only get in picofarads or nanofarads. All right, so capacitors of different types. Now, what is the action of the dielectric? What is the action of the dielectric on capacitors? Action of dielectric. So let's say we have the plates of the capacitor, and you put a dielectric material inside. And if you connect this to a certain voltage, say 12 volts, what will happen normally when you connect a certain voltage? Charges will sit here. You will get this one charged to some extent, and then this will be higher voltage than that, and therefore the charging will continue. You know, I told you that, right? The charging will continue. When will the charge actually stop? When this voltage is exactly equal to the voltage that. But in this case, there is an issue, which is the dielectric is also creating a potential difference on itself. So what exactly is happening is when you have these positively charged and negatively charged, the molecules and atoms here are going to realign to make it minus plus, minus plus, minus plus, minus plus, minus plus, minus plus, you know, like that, minus plus, minus plus, minus plus, minus plus. So these are getting polarized. When the dielectric gets polarized, the dielectric is creating a potential difference across itself. So there is a potential difference from here to here. I'll call it VD. But which end of VD is positive and which one is negative?
This thing is positive.
That one is positive and this one is negative. You can see this. See? Minus, plus, minus, plus. So at this extreme you'll have all positives. And at this extreme you have all negatives. Make sense? So there is a negative potential right there. There's a positive potential right there. In between you won't have any potentials because they can't cancel. So you have negative potentials here and positive potentials here. That is what is creating this voltage, VD. So even if this one gives it 12 volts, what is the net potential difference here? The net potential difference is this voltage minus that voltage, right? Because this is plus minus and that is minus plus. So the net voltage is equal to V minus VD. So when the net voltage is V minus VD, so the net voltage is V minus VD, and this is still higher. So even if this V is 12, and this probably is around 8, so what is going to happen? The net voltage will be like 4, and this will be 12. So the charging process is not going to stop there. What's going to happen? More charges will keep dropping here. More charges will drop here, thereby increasing the V. Will it increase this? Yes, that also will get increased. So both will increase to certain values. And when will the charging then stop? When V minus VD equals this. You get it? So by putting the dielectric, what is the consequence? Consequence is the charge that is actually sitting on the plates is going to be much bigger charge. It's not going to be just Q. It's going to be a much bigger charge. Right? So this is a bigger charge that is sitting here. So the bigger charge that is sitting there is CV. Because the net voltage is still 12. The net voltage is still 12. The net voltage is still 12. And until the net voltage is 12, the charging will go on. Which means this voltage probably goes up to 20. And this VD goes up to 8. So 20 minus 8 is 12. Then it stops. Make sense? So this V can go up to 20. And this one goes up to, say, 8. So 20 minus 8 is 12, and this is now 12, so then that is when it stops charging. Which means there is a chance of accumulating more charges on the same capacitor because of the presence of dielectric. Because of the presence of the dielectric, this is what is the consequence. So therefore, what is the new capacitance? It is a new charge over the voltage. And how many times is this capacitance going to increase? How many times? You know the equation for it. The equation is epsilon naught K area over. So previously it is epsilon naught A over D. Now it is epsilon naught K A over D. So is this C prime higher? Yes. How many times higher? K times higher. So this is going to be K times higher, which means Q prime is also going to be K times higher. That means if this was initially pulling up only 100 microcoulombs, with the presence of the dielectric, it will pull up 500 microcoulombs totally. You get it? So it is able to increase the capacitance altogether. This is when the battery is staying connected. If the battery stays connected, we call it online. So how the dielectric behaves online cases, this is how it is. Now let's go offline. What do you mean by going offline? You first connect it to the 12 volts. There's no dielectric here. There is no dielectric here. So the capacitance of this was C. Okay? This one's capacitance is C. It's just epsilon naught area over D. You connect it to the voltage. How many volts? 12 volts. So you put a certain voltage on it. You have already thrown a certain voltage on it, and then disconnect the battery. Remove the battery. So what will happen? The voltage will stay, the charge will stay, right? So the equation is C is equal to this. So the capacitance is Q over V, and the capacitance is equal to Q over V. And this is the status. Now, bring the dielectric. You're bringing the dielectric offline. Bring the dielectric and insert it right there. So if you bring the dielectric and put it there, because of the positive and negative charges already on the plates, what will happen to the dielectric? As usual, it gets polarized. So yeah, this one gets polarized with the negative here and positive here, VD. What is the net voltage? V minus VD. What will happen to the charge Q? Huh? From where? How can charge Q change? It stays the same. I've not done anything to the charge because I connected it and then it took it off. So I'm offline now. The charges, whatever charge is on the plates will stay intact. Make sense? The charge on the plates will stay the same. I'm not doing anything to those charges. By putting the dielectric, I'm not removing the charges. So the charge stays the same. So what is going to be the new capacitance? The new capacitance is the same old charge which is not changed divided by the, what has happened is the voltage changed. It was V before and now it is V minus VD. Here the charge changed, the voltage stayed the same. Here the charge stays the same, voltage is affected. So the voltage is reduced because of the introduction of the dielectric. So why is this capacitance changing? Because the voltage is dropping. If this capacitance is increasing 5 times, the voltage must have dropped 5 times. Right? Make sense? So the voltage must have dropped 5 times. That is purely because of the action of the dielectric. So you can have the dielectric offline, online. In both cases, the capacitance is going to be different. This is a new capacitance. The formula for capacitance is this. But how do you explain the capacitance going up? The capacitance goes up online because there are extra charges being picked up to compensate the voltages, to keep the voltage V. That's why the capacitance increases. Why is the capacitance increasing in an offline situation? Because the charge is not changed, but the voltage drops by a certain factor. And that's why the capacitance increases by that same factor. Yeah.
So there's no K in the signal?
No, K is the number of times it changes. So how many times is this capacitance increasing? K times. How many times is the voltage decreasing? K times. So the new voltage is going to be K times smaller. That is why the capacitance is K times bigger. The new capacitance will have K times bigger. Okay? Make sense? Energy of charged capacitors. Energy of charged capacitors. So if you're looking at if you have 2 plates, there's no charge on the plates. How much work is required to bring the tiniest charge and put it on the plates? How much work is needed to introduce a little charge on the plates? The answer is none. Why none? Because there's no potential difference. Because there's nothing on the plates. So to put the first little charge, you don't have to do work because there's no potential difference. Now, once you put a little charge on it, will there be a potential difference? And that means the next time you're bringing a small charge, you have to do work. And the next time you transfer again a small charge, you got to do more work. So you will be doing more and more and more work as you go on. That means, how do you find out the total energy stored? It is equal to the, so you are actually doing work. I'm doing both ways. You're doing a little amount of work transferring dq through a certain voltage which is existing at that time. This is not the maximum voltage. This is the voltage existing at during that moment. So if you want to transfer this information, dW is equal to Q over C, right? dQ. I'm changing the voltage to Q over C. Q is the charge transferred thus far, and C is the capacitance of the capacitor. Because you know the connection, right? Q is equal to CV. So V is Q over C. Now you can integrate it where the charge is going from 0 to Q, how much work is done. So if you integrate it, you're going to get W, the total work done. The limits are 0 to the maximum of Q. So Q dQ, how do you integrate it? Q, integral of Q dQ. Q square over 2, right? Right? And then of course the C is also there. So Q square over 2. And the limits go from 0 to Q. So if you apply the limits, when you put Q over there, you get Q square over 2C. And 0 gone. So that is the energy stored in a charged capacitor. The work done or the energy stored in a charged capacitor is Q square over 2C. But this is by using the integral approach. Now, if you want to talk in simple terms, not the integral approach, then this is how it is. This is Q and this is V. So for every dq, you know what's the relationship between V and Q? Straight line? Right? Now at this point, if you're transferring dq, how much work needs to be done is whatever small v is existing there times this. That's what I wrote here. See? The area of this rectangle will tell you how much work is required to transfer dq through that small voltage V. So how much is the work done initially? Nothing. The next time you transfer more area, you can see the area increasing. So now that is Q. You transferred Q coulombs altogether. So what is the total area? That will tell you the total work done. So the work done is equal to the total area. What's the total area of this? Half base height. Half base height. That is the energy. And you can replace Q with CV. You know Q CV? If you replace that, you get half CV times V. So it will be half CV squared. That's also equation for work. Now what if you replace V as Q over C in this equation? If you put this as Q over C here, then what do you get? W is equal to W is equal to Q square over 2C. That's what we got here. So we have three forms of the same equation. There are three forms of the same equation. Work done is equal to half CV squared. So if you know the capacitance and the voltage, use this. If you know the charge and the capacitance, use that one. Or if you know charge and the voltage, use that. So all this is referring to energy stored in the capacitor. All of them are talking about energy stored in the capacitor. Okay, any questions on this so far? And if you wonder, like your keyboard, every key that you're pressing on the keyboard, it's a capacitor. So, like the keys like that, when you press the key, it goes down, it gets close. What happens when it gets close? The area is, not area, the gap, separation becomes smaller. So when the separation becomes smaller, what will happen to the capacitance value? Goes up. When the capacitance goes up, what will happen to the voltage across it? Drops. And that drop of voltage is considered to be a signal. And that's how each one is configured. So when you're pressing a certain button, how does the computer know that you press that button? It's because the change in capacitance, and that is what is picked up as a signal. So every time you press those keys, you're sending signals through different wires into this thing, and so the analog input changes to a digital one, and then also your touch screen on your phone, it's a capacitance. It's a capacitive touch screen. It's a capacitive thing. So as soon as you take your finger right there, it changes the capacitance of that area because your finger is coming there. Your finger. You're not actually pushing it. It's not like a push, but the presence of your finger changes the capacitance. And so the pixels at that point will immediately convey the message that, yeah, you touched the cross, therefore goes away down.